And hello, welcome YouTube back to our turbulence modeling series, So we are going to continue our heat transfer bit with discussion on turbulent Prandtl number. So last video we were talking a little bit about turbulent Prandtl number for high Prandtl number fluids, and of course the low Prandtl number fluids as well. These ones are highlighting their average values, meaning to say, okay, if you have a simulation or what, and you want to use one Prandtl number for your whole simulation, assuming that Prandtl number is constant throughout near wall, in the free shear region, wherever, this is probably the correlations you want to use. Okay, what we did also before were the near wall models for Prandtl number for liquid metals, which evidently they vary with distance from the wall, and also the Reynolds number. Okay, so the Reynolds number and distance from the wall, that inevitably affects this turbulent Prandtl number. This Prandtl number is dependent on the Prandtl number and this viscosity ratio, the turbulence ratio of the turbulence viscosity to the molecular viscosity. So turbulence viscosity is in turn sort of dependent on the Reynolds number and also distance from the wall. Okay, so this is how it varies away from the wall, or towards the wall and then away from it. And if you want, again, a representative Prandtl number for their liquid metals for your whole thing, I mean this will be an average, then you'll use this this equation by Jishka and Reike, I think. Yeah, so I may pronounce their name wrongly, just pardon me if I do. I probably did, but yeah, this is the correlation they provide. And also, yeah, these were the correlations we discussed. I'm not going to go through them again. If not, you can go and check out the old videos. So now we have actually discussed turbulent models, turbulent Prandtl number models for Prandtl number over the whole fluid. Of course, we know actually your turbulent Prandtl number varies towards the wall. Now this may not be so important when it comes to force convection, because your boundary layers, they are very much driven. I mean the motivating force behind the flow is some pressure or some free stream velocity, but this will probably become more important in natural convection, because then the Prandtl number, or rather the heat transfer from the wall, suddenly becomes very important, because that becomes the driving force of the flow. And when that becomes the driving force of the flow, you got to get your boundary layers and everything correct. Okay, so when natural convection comes in, you got to pay attention a little bit more to this Prandtl number. Otherwise, in forced convection, you can sort of get away with it, and most of your CFD code would still give you more or less the right results. But just beware when natural convection is significant and comes in. You need to pay attention to the turbulent Prandtl number near the wall. So this is what this video is about. Of course, the liquid metals one we discussed, it's very important because they're low Prandtl number. So the turbulent Prandtl number will have a lot of Reynolds and Prandtl number dependence. And of course, distance from the wall as well. So for high Prandtl number fluids, there were tests run from Prandtl number equals 7 all the way up to 1000, and Reynolds number very high, 80,000 to 380,000. It's a very high Reynolds number, I guess. So what they use at y plus less than 5, they use a Prandtl number fixed at 1.07. That's fine. Nu T over here, strangely enough, I mean in the sublayer, maybe there is a little bit of viscosity, not a lot. This is how they model it to give it the right boundary conditions for y plus more than 5, I guess. So there's very little modeled turbulence viscosity here, though probably in reality you may or may not have it. It's very hard to measure because it will be small, it will be the laminar sublayer anyhow. So it'll be so-called growing with a cube of y plus, and it's 0.01. So 5 cube is 125, then you'll just get a nu T of 0.1 125 or something of that sort at y plus equals to 5. That will give you your correct boundary conditions to start in your next region, which is y plus more than 5. And y plus more than 5, then you use this correlation. This was a Kays and Crawford model, the original one. Okay, the original Kays and Crawford model. Again, it gives you a y plus dependence based on the nu t. Okay, nu t is dependent on distance from the wall, so that is dependent on y plus, and these are very important to get right. So this actually fits the data pretty well in this region. Okay, the mixing, how do you then determine nu t? Nu t is determined by some mixing length model near the wall. Okay, so you still have your du dy, sort of a strain rate, and then you have some mixing length. Okay, so together they form the coordinates of meter square per second. So this L is actually the use of Van Drijst model here, where L equals to the von Karman coefficient times y. Okay, von Karman coefficient times y. So this is not the y plus, it is dimensional. There is a unit to it. Then you have this exponential damping function, y plus over 25. So 1 minus exponential y plus over 25. This is then growing with y plus. Hold on. Yes, I think I'm missing a minus sign here. I've gotten it wrong while copying around these formulas from that paper. Yeah. So that means when y equals to 0, exponential of 0 is 1. Exponential of 0 is 1, meaning to say this term disappears. The mixing length disappears. Far away from the wall, you have this thing going to minus infinity. So this term should actually disappear, and you get kappa y. Yeah, so that's y plus over 25, and yeah, so this is the mixing length, which you will substitute in here to get nu t. So you can see nu t is already like a function of y plus, as you can see here, right? It's a function of y plus, and that gives you the y plus dependence on this, yeah, on this Prandtl number. So this is the Kays and Crawford model. It apparently works for Prandtl number in this range. Okay, so the above correlation fits well for this. Okay, but of course, the more models we use, the more complicated it gets. It kind of gives all of us kind of a bit of a headache. But anyway, that's just a comment. Of course, if it was possible to use one representative Prandtl number throughout, I mean, we would want to do that. Okay, so yeah. Anyway, these are I believe for pipe flow. So this is a forced convection kind of a thing. So do take note, forced and natural convection are a bit different. So yeah. Anyway, so we have more Prandtl number measurements, turbulent Prandtl number measurements in here. Again, these are using motor oil and water at various momentum thickness Reynolds number. So these are basically, you know, you have a U and then you have some characteristic length. Now the characteristic length here, I believe, is the momentum boundary layer thickness, I think. So this is how they calculate the Reynolds number. That's why this is so different from here. Okay, yeah, so anyway, I believe, if I'm not wrong, these are I don't think they are natural convection experiments, if I'm not wrong. Yep, so I think they are used for that. Pipe flow or internal flow kind of situation in forced convection, because the Kays and Crawford and Hollingworth model. So Hollingworth model is this one. Kays and Crawford's are this one, this model. These are generally used for pipe flow in a tube, not exactly for natural convection. But anyway, so we have this kind of correlation we are using. Again, for y plus less than 5, it is the same idea. Turbulent Prandtl number 1.07. Nu t is 0.001 y plus cube. and this correlation is then used. The Hollingsworth correlation is then used for Prandtl number y plus more than 5. All right. So this is the Prandtl number we use, and what this equation means is there's 2.76 like near the wall, but 0.855 far away from the wall, i.e. y plus more than 24. So actually what I've done here is to compute the Hollingsworth model from y plus equals to 0 all the way up. So this is very easy. You can just do it in Excel. You can take a look at y plus equals to 5. This actually has a Prandtl number of about 2.31. So I give you a scatter plot, and this is what it will look like. So the Hollingsworth model. PRT versus y plus. Okay, so this is what the model will look like. All right. Of course, I didn't use a log scale in here, so you got to take note which is a log scale, which is not. Okay. And now, of course, we have the mixing length model near the wall, the same. Nu t equals to some characteristic length scale square times the sum strain rate. And of course, you have your Van Dries relation here again, which I need to put a minus sign here. For lower Prandtl number water, the Hollingsworth equation doesn't fit perfectly. In fact, the Hollingsworth equation overpredicts T plus in a log layer by 12%. What is overprediction? So you can see this graph I have here. All right, this graph I have here. So if you have a T plus against Y plus in a log scale, and the brown curve represents your experimental data. If I say under prediction, the trend is usually like this. The gradient of this line is the same, but the intercept is different for the log layer region. Likewise, when I say overpredict, the T plus is actually more, but it's like parallel to the experimental data. So that's very important to take note of. So yeah, here's the picture I pasted here. So same idea. Yeah, overpredict and underpredict, same gradient, but not what do you call that? Yeah, not the same intercept. So that's what we have. So yeah, you should keep this in mind. And the question then becomes, if we don't want to use this model, what's the bad thing? How bad does it get? Well, you can take a look at this link online. I'll paste it inside the what do you call that? I can paste it inside the description. Yes, description. Okay, where am I scrolling to? Yes, I can paste this in the description. You can find it on Google Scholar. I think, yeah, you just paste this here. Alright, and then you will get this, it says a method of calculation of turbulent Prandtl number for SST turbulence model. This is K omega SST from St. Petersburg Polytechnical State University Journal. Click on this, it should give you this PDF. Apparently it's free. So what does the mismatch look like? It looks something like this. Alright, so it looks something like this. You see this under prediction. Okay, very much like what I'm showing you here. Alright, so I'm just gonna copy the citation and paste it here. So what happens if we do use it? Let's say for oil, if we use a Prandtl number equals to, let's say, 0.85, we observe a 15% under prediction for oil. 15% under prediction, meaning to say, if your value is here and you compare to the value here, the drop is about 15% from this experimental data. Of course, if you use it to measure against the T plus again. So if, let's say, T plus was 20 and then you have 15% down, so 20 times 0.15 will give you about 17. Okay, so that's where we get this drop. Okay, so 15% under prediction for high Prandtl number. Okay, so it's a 15 to 20% in this Prandtl number range, 5.63 to 6.19. And interestingly enough, at a water flow with even lower Prandtl number, there's a 5% under prediction here. Okay, there's a 5% under prediction of T plus. What does under prediction means? Under prediction means for us over predicting heat flux. Okay, under prediction means for us that it means over prediction of heat flux. So how do we come about of that? You can see what T plus is. Okay, let's take a look at T plus. What the formula for T plus is. Yes, this one. Okay, let's look for T star. Am I scrolling to? Yeah, here we go. So you're going to scroll all the way down and we see that, oh, okay, I am getting a, okay, so it's T minus T naught. It's a temperature difference over T star. T star, it has a few things in there. Heat flux at the wall, rho Cp and U star. Okay, so under prediction for us means over predicting heat flux at constant, at same, at a fixed temperature difference, flow condition. That means the skin friction velocity here. That's represent the flow condition, and same fluid because properties. Because we are talking about the same density and same Cp. Okay, so over predicting, at a fixed temperature difference, smaller T plus means the denominator is bigger. Denominator bigger means T star is bigger. T star is bigger means the heat flux at the wall is bigger. So that's what it means. Usually it means over predicting heat flux for a fixed temperature difference. And you can take a look at this PDF. It will show you pretty much the same results. 15 under prediction of so you see that yeah, you check this paper out, method of calculation of turbulent Prandtl number for SST turbulence model. Okay, this one actually gives you yet another model to calculate Prandtl number for your K omega SST model. Yeah, very similar in concept to what we have above, but they just have a new kind of model. Again, the idea is that when you get this under prediction of T plus, it means over predicting heat flux. Okay, so that's from the paper which you see here. You can see, take a look yourself. I'm going to show it too much. All right. Yeah, this is the effect of all this Prandtl number, and of course the effect of using a constant Prandtl number. And what you actually see here, yeah, there's a proper name for it. When you see this over prediction, under prediction, and yet the Prandtl number, the intercepts are different, but the gradient's the same. This is called log layer mismatch. It's very similar to the U plus log layer mismatch we've seen before if you've taken a look at my turbulence videos, other turbulence videos. But it's a different kind of log layer mismatch, and this is for temperature. And most of the time, if you use a constant Prandtl number, we will under predict T plus. That's for most what do you call that? Yeah, most of these correlations. Yeah, so PRT equals 0.85. It seems the estimate's pretty decent if you're not too concerned about over predicting heat transfer. But if you deal with convection, natural convection flows, it better be, it's better to be a little bit more careful with these things in mind. So yeah, in fact, why convection and mixed convection? Actually, these will help you set up very interesting flow conditions for your turbulent Prandtl number. Okay, and that's a whole nother topic on its own. But what I've covered for you, at least so far, is the forced convection turbulent Prandtl number, and what this turbulent Prandtl number does, and what I mean, I've also shared with you what if we use this constant Prandtl number at 0.85. Now, I mean, obvious, before I end, just want to make a comment. The obvious question is, can we change the fixed Prandtl number and expect the lines to kind of line up a little bit better? Answer is it's kind of difficult, because if you remember where we got our Prandtl number from, it is from dividing, okay, let's see, it's a du is comparing the gradients. If you remember this, how we derive this Prandtl number 0.85 is from getting this log law profile of temperature and log law profile of velocity. We differentiate both of these, and then we get the ratios between the two gradients. Okay, we get the ratio between the two gradients. So differentiating this, you get 2.075 over 1 over y plus. Differentiating this, you get 2.44 1 over y plus. And if you divide both of them through, you get the Prandtl number of 0.85. So if you change your Prandtl number to, let's say, 1, you would actually be changing the slope. Okay, if this is constant, then you'll be changing the slope of the temperature log law layer profile, and you're not really doing much to change the intercept. So it's not so simple as to say, okay, I want to change my Prandtl number to 1 or 1.2, and then you expect things to be different. It's probably not the case. It will not be the case, because what you are doing is you are changing the slope of this, and that may introduce some other unwanted errors. So usually to do this, to take care of this log layer mismatch, either you change your Prandtl number model in the log layer or across the whole boundary layer, or you can change the whole turbulence model itself. And one of these turbulence models which you can use in a DDES is called the Production Limited DDES by Ding, Wang and Chen. It was built to counter this log layer mismatch, especially if you use a constant Prandtl number throughout. Okay, but this is a hybrid RANS and LES model, so I won't touch on it just yet. In fact, before I touch it, I need to touch on the LES treatment of Prandtl number, turbulent Prandtl number. But yeah, there's a fair bit of ground to cover, fair bit of cases. So yeah, I'll stop for now. Thanks for watching. I'll see you guys again. Bye bye.